Hello, probats, and welcome to section 2 of chapter 4. This one here is all about adding, when to add and when to multiply. So make sure you have a section out, and let's go. And I hope you like this one. I hope you did well on your odds too. All right, so addition or multiplication rules. In a single trial, like if we have P of A, so we're finding probability of A and the probability of B. Okay, if they're completely separate, this is very important, they're called disjoint. Are not. So you take the probability of A or the probability if they are not disjoint. The probability of A in the first trial and the probability of B in the second trial, we use multiplication when they are not dependent. Probably A and B. So the difference is or and and. When you see the or, we're going to add, and when you see the and, we're going to multiply. All right. There's also a big difference between exclusive and not exclusive, but we'll talk about that. Compound event, we just have two or more. Okay, a disjoint or mutually exclusive. All right, that means they do not affect each other. All right, they cannot occur at the same time. Disjoint events do not overlap. So what one does has nothing to do with the other. Example, I'm going to select a person for a clinical trial who is a male, and I'm going to select a person who is a female. I cannot select them both for the same thing because one has to be male, one has to be female. They are completely separate. It's impossible to join those two. That's disjoint. All right, pause and see yours. Are they disjoint or not? Let's think about that. Let's randomly select someone who's taking class. I'm going to select Haley. Randomly select someone who's a female. I'm also going to select Haley. Are the events mutually exclusive or disjoint? And the answer is no. Because I can select someone who is taking stats who is a female. So they are not disjoint, okay? I can pick someone who is in stats and is a female. Not disjoint. If it was impossible to do that, then they would be disjoint. I hope you're understanding. Okay, addition rule. Love cards. So I gave you some pictures here. We want a P or B. Find the probability that an event A occurs or an event B occurs. So we're adding the single outcome and procedure. The or means addition. I want to find P or B. Now, add the numbers ways A occurs to the number of ways B occurs. So I want to find the probability of red or 9. Let's see how you do that. Okay, when I do this, the first thing I do is I say, hey, how many red cards do I have? And you should have came up with 26. Plus, how many 9s do I have? Now all I do is I count the 9s that are not in there. So there's 2 more. So the probability of this is 28 out of your total number of cards, which is 52. So you divide that. I am so out of room. I should have left myself more. So I have a 54% chance of selecting a red or a 9. The other way to do this is I have 26 red cards. I have 4 9s. So this is red, this is 9, and then you subtract the red 9s, which is 2. And you will get back to where you are. All right, try yours. Heart or a spade, and then a heart or a face card. Heart or spade. Heart and spades are completely mutually exclusive, so that's just 13 plus 13, which is 26 out of 52 cards, which gives you a 50% chance. Heart or face card. I have 13 face hearts. I have 3 face cards. No, I'm sorry. I have 12 face cards. But I have 3 face cards that are hearts. So this is hearts. This is face cards. This is the heart face cards. And you get a total of 21 out of 52, which is a 46% chance. All right, let's go down here. This is just the formal one. Probability of the first plus the probability of the second minus where they overlap. All right, let's see if you got this. Red or 9. So let's do our reds or 9. We had 26 out of 52. We have 4 out of 52. You notice I just put the 52 in at the end, which is fine. I have 2 red 9s out of 52. And that's how we came up with 28 out of 52. All right, we've already done these two above, but you're welcome to do them again. Remember, the complement of event always adds to 1. Let's do an example of that. So let's say I wanted to know the probability. Let's look at the first one. Come on. There goes. Probability of not getting a red or 9. Well, since I already know the probability of getting a red or 9, I take 1 minus that probability. And that equals 24 out of 52, which is a 46% chance. All right, let's go down here. A and B are independent if the occurrence of the one does not affect the probability of the occurrence of the other. That's independent. All right, dependent, when they are not independent, then they're dependent. So whatever I do to A affects what I do to B. And we calculate these differently. Let's do a multiplication rule. Probability of A and B both happening. So when I say and, I want them to both happen, which means I need to multiply. So we take the probability of the A and the probability of the B, and we multiply those together. This is read the probability of B, given that A has already happened. This is very different. So I check at A, this is what I'm dividing by, and then what's the probability of A, B happening given that that has happened? And we'll show you some of these. I don't ever use the formal rule, but that's okay. 50 test results from the subjects who have COVID are shown below. I have positive test results of 32, negative test results of 18, which gives me a total of 50. Wasn't that a nice number I came up with? Okay, 2 of these people are randomly selected with replacement. Very important. That means I put them back. So the probability of it being positive is 32 out of 50. The probability of negative is 18 out of 50. So I want to know the probability of the first being positive and the second being negative. Since it's with replacement, it doesn't affect each other. So I just take the positive times the negative to get my answer. So this means I have a 23% chance of getting 1 positive and 1 negative test result from 50 people. Okay? Now, I want you to pause and tell me the probability of getting 2 correct tests and 2 false tests. Okay, I hope you did a good job. You should have just multiplied them together. Now, remember that was with replacement. Okay, same data, same 32, same 18, same 50, this time without replacement. So that means they affect each other. So when I go down here, I want to find the probability of a positive and then a negative. Well, the positive is 32 out of 50 because that's the first one I'm drawing. But now the negative, I don't have 50 left. I only have 49 tests left to choose from. So since I did not put back the first positive, this is how many negative I have left. Multiply that out, we get 0.23, which is a 23.51 chance of happening. Now, pause and do your two positive. Okay, I hope you did a good job. On the positive now, both of the numerator and the denominator are affected. Because if I choose out of 32, I only have 31 positive results left. If I take away 1 from 50, I only have 49, which gives you 0.41 or a 41% chance. So remember, very important, with replacement, independent. Without replacement, they are dependent upon each other. Very, very important. So read carefully when you're doing your homework. All right, we still have a 5% guideline. Now, for cumbersome calculations, they kind of cheat a little bit. Okay, without replacement, the sample size is no more than 5% of the size of the population. So we have a very small sample size. We treat the selection as being independent even if it's not. Because it's such a large amount, it's not going to make a difference in the end. So without replacement, we're going to talk about the adults in the United States. Well, there's 247 million of them. Assume that 10% of the adults in the United States use drugs. Find the probability that 3 selected adults will use drugs. Now, technically, that's dependent, because if I choose one, he's no longer left to be chosen. But since it's such a large population, and we're only choosing 3, which is so small, we're going to treat them as if they are. So we just take uses drugs, and uses drugs, and we multiply those 3 10% up to get our 0.001 probability that all 3 use drugs. All right, pause and do yours. Uses drugs, we knew was 10%. Uses drugs, we knew was 10%. Does not use drugs. Well, that's the complement of using drugs, so that's 1 minus 10%, which is 90%, which goes here. So our probability is 0.009, that you have 2 that use and 1 that does not. Making sense so far, right? Nothing too major. Okay, the principle of redundancy. So this is what a lot of engineers use and people who design things. So redundancy is like we create like a fail-safe. So I want to make something more reliable. So if I know something can fail, I create like a second one that will replace it. So if it fails, it's not a big deal. So let's go down and read this. Okay, Airbus or an airplane, twin engine. There's 3 independent hydraulic systems. So if one system fails, the full flight control is maintained. Because if there was just one, if it fails, you're not going to do well, right? So the failure of one hydraulic system is 0.000 or 0.002. Not bad. Okay, so the probability that it does not fail is 0.998. I have 3 of them. So the probability of all 3 failing at the same time, because I can still run the plane with one of them, is 0.02 times 0.02 times 0.02, which means 0.000000008% of it failing. I have increased this tremendously because now the odds of it not failing went from 0.998 to 0.999999992. This is amazing. Our safety has increased drastically and we are happy. So where we were divided of where we are, I've increased my safety by 1 over 25. I think that is incorrect if I remember right. Yeah, this here comes out to be 250,000. Sorry, I typed that in there wrong. Times better. So I've increased it huge. It's a wonderful thing. All right. I made up an example for you that I want you to do, and I forgot to type it in here. So you're Explorer. I want you to do the same thing, but now I want you to do it for 4 hydraulic systems. Okay, pause and give it a shot. Okay, I hope you did well. Probability of all of them failing is 0.002 times itself 4 times, which is that number. All don't fail is 1 minus. This is like an at least problem, just so you're aware. So 1 minus this amount gives us 0.999999984 chance that they will not all 4 fail, which went up even higher than before. I hope you did great. All right, I hope you do well on your homework. I want you to do Chapter 4 survey, question 2. Calculate the heads, the month, January, February, or March. All right? So, heads or tails you flipped. When were you born? Okay? Probability from the survey, questions 3 and 4. Two-way frequency tables. I'm not real sure if these are 3 and 4 anymore. On page 148 is where you can find a frequency table if you need to learn how to do that. And I want to know right in female, right or female, right given that it's female, female given that it's right. And we will probably have to talk about those, but I want you to give it a shot. Okay, good luck.